Hello, in today's lesson we will talk about some common terminology that will be used specifically for databases and database technology in specific. Um, this is just kind of an overview background of what databases are and how kind of this stuff works together. So, that said, I am your instructor still, and we will be moving along. So this is lesson 2 on terminology. So what is a database? There's several definitions. We'll just kind of highlight a few of these. Database is a collection of related data organized for quick access. So we store a lot of data so we can get to it quickly. And that's what a database does. It's organized by rows and columns into a table. Oftentimes the data is in-depth so we can quickly retrieve the data and to ensure its accuracy. Databases handle the insertion, updating, and deleting of data. And databases process workloads or jobs to update themselves, query the data, and run applications using the data. And kind of a bland definition, but that's what databases are. The databases take various shapes. One shape is a data warehouse. A data warehouse is a historical data captured from various sources and is consolidated into a central warehouse. The process of doing that is usually called ETL, or extract, transform, and load. So it extracts data from various sources, it'll transform it, and then load it into a data warehouse. Once we have data in a data warehouse, we can then use data mining to analyze the data, typically from one or more data warehouses. And we're looking for statistical trends, things that can help us run our business better. Now, I saw a couple of examples. Oh, this is probably back in the 2007-8 timeframe. So an example of some data mining. It was put out. I thought it was impressive. One was they took a customer sales data. It's a website, and they took data from the website, and they ran it against some data warehouses that they had already collected outside of the customer's data. And from this, they were able to do an analysis of the people who were buying from this website. And they found that they tended to be educated men in their 20s and 30s. Now, once they had that data, which the owner of this data had no clue. He said, I'm just selling stuff. He said, I didn't know. But they actually took the sales data, ran against other sources, and said, no, the people who are buying from you tend to be educated men in their 20s and 30s. So with that information, using data mining, the owner is able to now target specifically the demographics of people who are buying these products. And by doing that, instead of just broadcasting wildly out there to say, marketing wildly to say, I hope people who are interested in this stuff find it, they were able to target educated men who were in the 20s and 30s. And so this demographic tends to go to these websites such as ESPN and whatever. And they were able to then target their marketing towards that. And from that, their sales increased significantly. They can also use that and say, well, we want to attract a different niche market and maybe change their products to do that. They didn't do that. They were going after their core demographic, and using data mining, they were able to do that. Another example at the same conference was Starbucks. The company, not Starbucks, they were just demonstrating how data mining works. They took went to Austin, Texas. Well, they went to the Starbucks that were in Austin, Texas, and said, what do these Starbucks have in common with each other? And they were able to identify demographics of the neighborhoods that Starbucks were operating in. And because they were not part of Starbucks, they did not know which ones were successful and which ones were not. But using this data, they were able to then look at the general population geographic area of Austin, Texas, and said, okay, Starbucks tend to be in places where, I can't remember what the demographics were, but these types of neighborhoods, they said, okay, now go out and find those types of neighborhoods, those types of places that don't have a Starbucks. And they identified 4 or 5. From that, they said, okay, from here, which ones have stores for rent or places to locate? Again, they squeezed it down, found 2 or 3 of those locations. And then they said, okay, which one of these would be appropriate, which ones would not. They, there's some other data mining, eliminated those. They said, here are 2 places that would seem to be good models for Starbucks. Interesting concept. Again, they were not part of Starbucks. They were just showing how you use data mining to find places that were conducive to having Starbucks that didn't have one. I thought it was interesting. Anyway, that's what data mining does. We'll move along here. Relational data. Now, this course is going to focus on relational data. This is transactional data. It's the most popular model because it handles transactions kind of in real time. So you update it, it's updated immediately. Now, this does not fit every situation. For example, Facebook, Twitter, some of these places, sites like that, things don't have to be instantaneous. You may think it is. If you post something in Twitter or post something on Facebook, it may not go immediately. It may appear to you, but not to the not to the world. So it may just be a block of people who see it. Eventually, everybody sees it. They're not exactly trying to get real time, but the relational data model, we're trying to make sure that when you post a payment in a business application, that payment is real. It happened then. Anybody else trying to look for that will see the same consistent data. So that's transactional data. This was formulated by a doctor of mathematics named Dr. Codd. He was a fellow at IBM several years ago. They asked him to take a look at data and see how we could do it. Being a mathematician, he obviously came up with a mathematical solution, and that was kind of the birth of relational data model. This was back in the probably 1960s, and it's still being used today. That's what this course is about. So it's not many things in IT last for 50 years, and this is one that did. Again, this is not for every situation, but it's for many or most situations. We focus on that. Now, relational data uses the ACID or ACID model. Let's briefly look at that. We're not going to spend a lot of time on this, but I just want to mention this term in case you run across it somewhere else. So ACID is 4 components. Anomicity states that database modifications is all or nothing. If one part of the transaction fails, the entire transaction fails. So it all must work together. The C stands for consistency. States that only valid data will be written to the database. So if you in a transaction that is violates the rules of your database, then you can be assured that that data will not be inserted, updated, or deleted because it would leave the database in a inconsistent state. So if you do that, the data will be rolled back to a consistent state. Once, if your valid data does not violate the rules of your database, it will be written and your data will transform from one consistent state to another consistent state. Okay, so atomicity, consistency, isolation requires that multiple transactions occurring at the same time will not impact each other's execution. So if I have two transactions going at the same time, this will ensure that one will execute without depending on what's happening in the other transaction. In other words, basically we're going to single thread these things in a sense so that the first transaction goes through, and then the second one goes through. We don't determine which one goes first or second, which is saying that both transactions will be executed independent of each other. And the D stands for durability. Says that a transaction, once it's committed to the database, will not be lost. We will have backups, we'll have transaction logs, we'll have various components built into the database that ensures that once we have a transaction committed, that it will not be lost. So those are four important components of databases called the ACID model, ACID. Now let's talk about data consistency. So if we have a good design, we want to promote consistent data. We have problems when we have inconsistent data. For example, if I have a balance, I go one part of the application that says my balance is $100, and go to a second part, the same application at the same time, and it says, oh, my balance is $200, which is correct. Is one correct, one wrong, both wrong? I don't know. So we want to ensure we have consistent data. Once we start having inconsistent data, our users begins to lose faith in all of our data. And once they lose faith in all of our data, or in any of our data, they start losing faith in our application and our website. So we want to make sure we have a model that provides for consistent data, because how can I trust your website, your application, if the data is inconsistent? All right. Another thing we want to avoid is data redundancy. So the best way to promote data consistency is, I don't know, let's store data only one time. If you store data, then we don't worry about inconsistent data, because whether it's right or wrong, it's the same everywhere we go throughout your application. All right, so duplicating data does not make it better. Storing it twice doesn't make it better, doesn't make it more durable. Remember the ACID model says data is going to be durable anyway, so we don't need to store it multiple times to make it better or protect it or whatever we want to think about. If anything, storing it multiple times makes it worse. Because now when we go to update data, if we don't update it everywhere, we will go back to our inconsistent data problem. All right. So why risk it? And one last point to make is redundant data is expensive to store, it's expensive to back up, and it's expensive to recover. So there's no value in duplicating data. It gives us inconsistent data, or could, and doesn't make it better. It introduces problems that we don't need, and it can add expense to our cost. All right, third thing we try to avoid with a good model is we don't want to have any missing data. Data that is missing cannot be used. If I only store courses that have students enrolled in it, I have a lot of courses that I can't show people because they haven't enrolled, which is, I don't know, catch-22, in that they can't enroll if they don't show up. So we will make sure that our model promotes universal data so that the data will always be there. All right, so ideally we restore all the data, and we won't have redundant data, so we only store the data one time. Again, this comes back to the issue of making sure our users do not lose faith in using our application. If we have missing data, they're going to question the entire application. And I mentioned in the previous lesson that good applications begin with data, making sure your data model is accurate. Without that, no matter how well you design your systems, people are not going to have faith in it if we're having these kind of problems. All right. We need to talk about database management systems. Database management system is a collection of programs that store and modify our data, provide security, extract information from the database. There are several examples of DBMSs out there. Some of the more popular ones are Oracle, SQL Server, MySQL is an open source database. It has some spin-offs from that. And also Microsoft Access, as much as I detest that system, could be considered a poor man's DBMS. Now these DBMSs are big, hairy, complicated systems. A lot of these are more complicated than operating systems such as Windows, for example. If you go by lines of code, DBMSs tend to have half again as many lines of code than a operating system does. Just to give you an example of how complicated these databases are. These DBMSs are. All right, another term you may hear throughout your data career, application development website career is metadata. Metadata is just data about the data. It's used in several ways. For example, HIPAA uses it for privacy. It's used for security. Audit logs store information about the data. They like to know when the data was created, who modified it, when it was deleted, and of course, who did it. So it's data about data is metadata. It describes the contents of the data in the database. All right, let's talk about entities. An entity is a person, place, thing, or event. So a person, example of a person would be students, teachers, taxpayers, coaches, singers, musicians, homeowners. These are people, and they are a type of entity. Places are another type of entity. Examples of places are buildings, stadium, school or classroom, courtroom, resort, doctor's office, hospital. These are places, and they are entities. Things are the third type of entity. These could be things include stuff such as computers, sales orders, purchase orders, a test, a project, automobile, various modes of transportation, airplanes. These are things, and they are things that we track as entities. And the last one are events. Events are things that happen. They tend to have either a date or a time associated with them, such as a birth, a graduation. In sports, we have games. It could be an accident, when the accident happened. Concerts, talked about musicians earlier. Concert is an event. And my favorite, of course, is vacation. I like my vacations. All right, so entities are composed of things that describe the entity and we call these attributes. So if you look at the student we had from the previous slide, students have attributes such as name, birth date, address, email, credits. Remember lesson 1 we talked about GPA? GPAs could be an attribute of a student. These are things that describe a student. So once we have a student entity, we would then know the student's birth date, maybe graduation date, address, email. We would know those things about the student. Attributes equate to columns in a spreadsheet. So if you have columns, they tend to be the vertical things that describe something about whatever we're doing. In the old days, we had flat files. We call these fields in a flat file. So I have a question for you. If the attributes are the columns of a table, what are the rows? So imagine a spreadsheet. We have columns here that describe things. We have, like we said before, birth dates, graduation, GPA. So the rows then are the horizontal, the individual entries or instances of an entity. For example, if I have an entity for student, each row represents one student, such as Sue, John, Mary, or Chris. Each row represents a student. Within that row, we have columns that represent their birth date, their name, their address, email, so forth. It's that where those two things join together. Then we talked about the data context in lesson 1, the 3.5. So now we have a column for GPA, the row for Sue, and 3.5 now represents Sue's GPA. That fits together? All right. We have entities. Entities are related to each other. There are several types of relationships. A one-to-one says if I have two entities, one of these has one of those. A state has one capital. A capital has one state. One-to-one. One-to-many says one of these has many of those. For example, one state has many cities. Virginia has Richmond and Virginia Beach and Alexandria and Roanoke and Blacksburg and Charlottesville and Williamsburg. Each of those, so a state has many cities. Now each city has only one state. Richmond is in only one state. Williamsburg, one state. So one-to-many relationship. We're going to get more into this when we get into data modeling. I'm just right now teeing things up by giving you some definitions. The third type is many-to-many. Many-to-many says one of this type of entity can have many of that type of entity. One of this type of entity can have many of that type. For example, a state can have many businesses in it. A business can be in many states. Okay? So the relationship between state and business is many-to-many. A couple more things we're going to discuss. And we'll get more into this later when we get into data modeling. But be aware that there are things called strong relationships. A strong relationship says, I cannot have a row in this table that relates to a row in that table unless it exists in the other table. For example, if I have a table here for students enrolled in a course, that I cannot have a row in that, we call it roster, I cannot have a row in the roster table unless the student exists already. And this course exists as well. Those are two strong relationships, meaning that a row in the roster table cannot exist without a student and a course. A weak relationship says an entry can exist if it is not in another related entity. Going back to our student roster example, I can have a student exist even though there are no rosters items for that student. I mean, the student exists independent of the roster. So if I have a system here, a student just comes in and says, hey, I want to be a student in your college. Great, we'd love to have you. We're going to add a row in our student table, even though there are no corresponding rows in the roster table. That's called a weak or non-identifying relationship. I know this is a lot I'm throwing at you right now. Don't worry about if it doesn't all make sense to you. We're going to spend more time when we get to data modeling to go over this in more detail. I just want to throw these terms out there to you. All right, so now we have entities, we have relationships. We now have something called an ERD, an Entity Relationship Diagram. We'll have a whole nother lesson on how to build entity relationship diagrams. I'm just throwing this out to you now so you can see how this fits together. Okay? I want you to see how this works so that we have entities here for course, instructor, office. We have a fourth one called instructor course. Course has attributes of name, credit. Instructor has attributes of first name, last name. You can see how we can have a diagram that visually depicts our entities and the relationships and attributes of them. Don't worry right now. We're going to spend a lot of time doing these in the next few weeks. All right. So that's another term you may see. A view is a virtual representation of physical data. So we have several entities. We take parts of these entities, these physical entities, take parts and piece them together, and we can create a virtual representation of that data. Don't worry about it for now, I'm just throwing the term out there. Okay, actually, in the course after this one, we'll spend a lot of time talking about views and how to create them. But for now, it's beyond the scope of this course. All right, database types. We talked about relational databases and transactional databases. We did talk about, but there's another one called object-oriented, which brings in the processes that we act upon on a entity within the database. And we did talk about historical or data warehouse databases. Again, in this course, we are going to focus on relational and transactional data. Not saying the others don't exist. This is the most common one, and usually for business use, agency, organization use. Most of those use relational and transactional databases. All right, so this is just some general terminology that we will use in this course. We'll use in this course. We'll get more into specific terminology coming up in some of the further lessons, especially when we get into data modeling, entity relationship diagrams, and things of that nature. So I hope you enjoyed this, or maybe not enjoy it, but this is the background to it, and we'll get more and more into this. So that's it for tonight or today, and we'll see you next lesson. Take care.